So well, we will see the thing about the Borel measure, the open sets, the counter image are Borel sets later, because we need it. We do an extension with respect to the theorem in the book. So today we introduce what is a measurable function. So up to now, what we have a space, which in our case is R, and usually we see this notation. So it's R, so this is the space. Then we have a sigma algebra, which in our case is L, so this is the Lebesgue sigma algebra, which is easily seen is the Borel sigma algebra. So Borel, what we saw, plus the sets with measure 0. Okay. Actually, we just did the G delta sets or F sigma sets. And finally, we have the measure M, which is the Lebesgue measure. So this triple is a measurable space, is a measure space. While the first two are what is called a measurable space, something you can put a measure on. Okay, so let me give you the fundamental thing to say what is a measurable function. So let's say if A is in N, so it is measurable, I certainly want to have the following equivalence, that the indicator function of A, which is 1, 0, is measurable, is a measurable function. Do we agree on this 0 step? So if I don't have this one, well, there is a little bit of trouble now, because of basically the algebra, so between indicator function, or if you take the supremo of the indicator function, or the maximum is like the union, the infimum is the intersection, the product is the intersection. So essentially, well, if you want to have some measurable function, you have to pretend that this holds. Otherwise, you are going to construct something that is inconsistent. Okay, so let's see now how to say this object here. And then I make a digression again. Nothing of this thing is in the book. I'm just trying to let you know why it is natural to go in one direction. So now we start with the Riemann integral. I said I'm not going to touch this too much, but I think here is needed. And then here I put what would be the Lebesgue integral. So I'm giving you a function. So how to construct, well, okay, let's do it. How to construct the Riemann integral here? No, you partition which part, which set? So the F or the X?
The
X. Okay, so we do like this, stripes, and then basically approximate stripes with rectangles. Okay, the Lebesgue integral, you invert the vision. Because we have a very good notion, but here what is the problem? The problem is that it depends heavily on the function. You have a convergence. And the convergence should be respect to the construction you give. It's a series, you want a series to converge. While here you have a very good notion on measure sets. So you can give, so let's change now the vision. I don't have color chalks. That's how that's in the back. Well. No, okay, I just had X. Let me do it.
Somewhere.
So you know. This you know. So on the other hand, I can, since I want to measure the area, well, let's do the opposite. But basically, okay, thank you. Maybe. So, what is the difference now? The difference now is that instead of multiplying the length of this fixed size partition, I multiply the height here, which is my fixed side 8 side, times the measure of which set. For example, here is the measure where the function is, well, you see, here I approximate. So here I approximate. Here is the function is larger than this value. So it's something like the sum epsilon times the sum, the measure of the set where f is larger than, well, my I epsilon. More or less, no? Because I usually, well, the thing is that clearly I have to do some way to smooth out or well, depending on where you see it. In any case, I have to compute what is this object here. Then I decide either is I take only the epsilon value, or I take this value, I take the other value, doesn't matter. The important thing is that this size is fixed and does not depend really on the function in some sense. What it depends on the function is the measure of these sets. Okay? Okay, so now we have to fly a little bit and understand what is now is almost written there. So when I can call a function measurable or Lebesgue measurable. And people here they know, but I'm asking people they don't know maybe. So let's see. So here I have to pretend that this object, and this is the indicator function of where f is greater than I epsilon. So I'm giving a value to indicate.
Excuse me, what is I?
Well, I is in R because you have a partition. So this is I minus 1 epsilon, I plus 1 epsilon. But you can even have different sizes, doesn't matter. Like for the Riemann integral, doesn't matter which is. Just you control that the size converge, the maximum of the size converges to 0. Okay, so let's rewind everything from backward actually. Okay, so I want to compute in this way the integral. This object here is something like giving the integral of the indicator function, because it's the set or well, the region or whatever, the set where it is larger than my value I want to do, of my partition, the value of my partition. But this should be measurable. Then I want that if this is measurable, essentially I require that the set is measurable. So very easy. So since this epsilon I will become everything, now we can give the definition. So f. One notation. So one just observation. Usually, since here we can work even with f equal to plus infinity. For me, it's fine. The only thing is that clearly, once you have f plus infinity or minus infinity in sets which is measured non-zero, well, it's like something like to add plus infinity and minus infinity to r and computing the algebra. No. So okay, you cannot sum minus infinity with plus infinity with minus infinity, and you have to be careful about a little bit the inversion, or 0 times infinity, all these things over there. So I prefer to not to have additional heavy notation, because the case where f is plus infinity on a large set, well, you can compute as a particular case. So we take this value is in R. If for any reason we get plus infinity, well, it's something we will add case by case. Because otherwise I have to ask here something R union plus infinity minus infinity, and then I'm going to bring it, or I just have to add R bar and go into the end. But you understand that it's just a limit case, no? If you know how to handle in R, you know how to handle in any situation. Because that is just, when it's plus infinity, you have to be careful on not to have this situation where you cannot decide what is the sign. So here for R, let's say for R. It is if is measurable. And let me introduce another notation here. Measurable is for this set, for this situation is L0. 0 means measurable, because if you add something here means that the integral, so this limit, this operation passing to the limit, is bound with some power. So let's say that this is L0. Okay, let's look at the position. Here I have f larger than a given value. I can give a value with respect to the measure. So let's say f to the minus 1, c plus infinity is in the sigma algebra. So you see, it's very natural. Once you think the integral in this way, okay, once instead of seeing vertical stripe, I see horizontal stripe, it's very natural. And the power here is that, well, the heavy part of the computation we did already when we built the measure. Because we have now a lot of wide sets to which I can give a measure, and before, well, you know that the functions that for the Riemann integral are not so many. Basically, continuous function that vary up to a set, as countable set, more or less. Okay, so now let's work a little bit with this definition, just to play a little bit the game. Aim is to use now the sigma additivity, or the sigma, let's say the sigma closure of the sigma algebra, in order to change a little bit the quantities here, no? So for position, so f is in L0, so it's measurable, Lebesgue measurable. If, so this is equivalent to, if any, let's say, any of the following condition holds. Okay. I think the proof you can just say f to the minus 1 c plus infinity is a measurable set. You know how to do that? You see how to do that?
Yes, probably. There is this union.
So
interval.
Exactly. C plus infinity is the intersection C minus 2 to the minus n plus infinity. The intersection. And then, okay. So let's do proof line by line. So now what I do?
Apply
F to the minus 1. This is the intersection of F to the minus 1. And that's, sorry. And this is the sigma algebra. The sigma algebra is closed, is a sigma algebra, so it's closed for countering many operations in the algebra, and then I'm fine. Okay, now suggest some variation. Yeah. There are many. We don't need to follow the book. We can invent how many you like. So, for example, let's see.
Between the values between two different.
Yeah. That's the one of the most important. How? Complement più intersection.
Yeah.
So let me put here first the complement then. That's complementation because this is it's R minus so this is and that's the complementation. And then this is the intersection, no? Okay. And then, well, another one. Closure. And okay, that's like this is the inverse of the original one. So let's keep also a guy here that I put here. So f to the minus 1, c plus infinity is L. And let me give you some corollary. So f to the minus 1 of a point. Actually, I have to prove this is in some way, at some point I have to come back, no? So let's see the line. So from measurable I obtain this guy. From this guy by complementation I obtain this guy. From this guy by intersection this guy. And this guy I obtain from, well, I can take the, well, from this guy I should obtain, so at some point I have to close the loop. So which one you want to, from which one you want to close? Well, let's say from this guy up to this guy. How to do that?
From B to this?
From B to this, yes. Just because I said that they are equivalent.
Because we can take C plus infinity equals union
C
union A plus 1.
Yeah, A n plus 1. Well, A, let's say A and N, let's say. A plus 1. And then?
Yeah, A plus 2 plus.
Then you have the walls?
Yes.
Ah, okay. A plus, okay. A plus N.
Yes.
Okay, so we close the loop. Is that true?
Yes, because we can use D and A.
Yeah.
Intersection.
So it's C plus infinity intersection minus infinity C. Let's see. And now, can from this one close the loop?
Yes, because every union is just every interval is just a union of these singletons.
How many? No, you cannot.
Yeah.
This is not sufficient. I think, let me see. I want to give the example now. So let's see an example. Okay, so let's take the usual define. So usually we have only one set, no? Only one non-measurable set up to, well, resizing and transformation is just one non-measurable set. F is equal to x if x is in Z and Z not belonging to L and 0 otherwise. Otherwise, and Z is contained in 0, 1. We have one of these sets. Was one of these strange, let's say, non-measurable sets we built by equivalence relation. Okay, so clearly the counter image for any, well, actually I have C0 here, which is a problem because, so let's say minus x. In 0, 1. So for any point is mapped up to x, up to minus x, and in 0, 1, then since Z is not 0, so you have only one counter image.
Sorry, points outside the unit interval.
Okay, you can say they are 0.
They are mapped to 0?
Yeah.
Okay.
Because then it is the unit interval plus 0. So it's the complement of the unit interval plus 0, so it is measurable. But you don't care. If you give a measurable set, you can always extend to 0 outside and still the function is measured. So this is a function so that the counter image of each point is 1 point. However, the counter image of the set 0, 1 is Z, which is not measured. You cannot deduce measurability by just looking to 1 point. If you remember, the integral, indeed, you need a stripe. And the stripe is here. Okay, but let's relax a little bit. So we erase the corollary, we add another point. The measurability. For all open, and actually when we say that for all Borel, later, set f to the minus 1 of O is measured. So the idea of so our aim now, we have the measure, we have everything, is to see that with this interpretation, this definition of measurable functions, we have a lot of freedom. So a lot of sets have a counter image which is measurable. And at the end, the idea is that the Borel sets, so not only the open set, that's a counter image which is measurable. Okay, so let's fix the proof for Borel. Let's do the proof for Borel. I'm sorry. Actually, no, you do. We just speak about the proof of Borel.
Sorry, just for the setting, f is also measurable function.
Yeah.
Okay.
Yeah, only to say this. So let's do the proof for open. Somebody will give the observation that open, how much matters for to be in R, because open sets are a union of countably many intervals. No, well, here it matters if I want to have this definition.
So it is Borel, so it is just a measurable set and excluding a countable number of points.
Well, which one?
A Borel set. O is
Borel
a
set.
Yes.
It's
a measurable excluding countable number of points, right?
no. Well, actually, you say in the opposite because the measurable sets are larger than Borel sets.
Oh, yeah.
So usually you can say that any measurable set is a Borel set plus a set of measure zero.
Yes.
But the sets of measure zero are not countable because the power set of a set of measure zero, so all the subsets, is still measure zero by monotonicity.
Yeah.
And since you have a set of measure zero which is not, well, actually you have a set of measure zero which is countable, then it is uncountable. You cannot say what is the cardinality unless you have to assume some additional axioms, but certainly is not something, it's not countable that you can deduce without any effort.
We can prove that for open sets and closed sets, then f delta g, f sigma g delta, and so on to prove.
But you call open sets? Well, you have this guy, and I was just thinking something easier. So you said that open sets are, especially in R, are countable union of disjoint intervals.
Yes.
So the counter image of an open set will be the countable union of disjoint counter images, and counter images are measured. So in general, so now let's open up parentheses. I'm sorry, I prefer to, because otherwise it becomes boring. So what is in general space? What would be, in your opinion, among these definitions, the one that can be passed to a general situation? Because this is something
proposition. That,
yes.
For every
counter image of open sets is measured. But this, because in your, if you are going to work, this is the standard question. So how to give a definition which works in general, starting from the example that you know. At some point you deduce something which can be transferred to any setting. And this is the setting. So if you have a topology here, you would say that the counter image of open sets are measured. But this doesn't make it easier to find the integral, of course. So that's another question. Okay, so let's prove for Borel. And now I'm sorry, this was the point I missed last time. But this is quite easy. Well, it requires a little bit more effort. So let's say that. So take the sets, which is A, the family of sets A, which is f to the -1 of the Borel sets. Okay, so A is a sigma algebra. Okay. And now take the family of counter image of open sets. So let's say B is f to the -1. Well, we need just open or intervals. Open set. Now what I'm saying is the following. So, well, now we consider the sigma algebra generated by B. Okay? So let's say, let's call it M is the sigma algebra generated by B. So the statement is that B is equal to A. Sorry, M is equal to the family A. And this is also why the continuous function, the counter image of Borel set for continuous function is Borel sets. Because, so the corollary of this setting is that f continuous f to the minus 1 of Borel is Borel. Simply because this one is open, B is contained in the open sets. Okay? And then the sigma algebra generated by B is contained in the Borel sigma algebra of R. And since I know that the counter image of the Borel sigma algebra is the Borel sigma algebra generated by A. Okay, I'm sorry, I know that it's a little bit more tricky here, the reasoning. So let me repeat the reasoning. General statement. This is general. Take a family which is an algebra or a sigma algebra. Take the counter image. Take the generator of the algebra. Take the counter image. Take the algebra generated by the counter images. It's equal to the counter image of the algebra. So, or I can do the following. So let's say you have A, so you have O, which generates B. Here you have f to the minus 1, which give a family, let's say B. Okay, this is calligraphic B. And here you have f to the minus 1 of this set. And here you have the counter image generates. And so the diagram is commutative. So let's go m f to the minus 1. So m equal to this A, but A is the counter image of B. Okay? So this is the general statement. How to, for f continuous, let's apply for f continuous. Counter image of open is open, so sigma generated by open is Borel. Counter image of open is a subset of open. Sigma algebra generated by open is Borel. So the counter image of Borel is a sub-sigma algebra of the Borel sets. I'm not saying that is it's just sub-sigma. Okay, so how to see this fact? This fact is because the operation of the sigma algebra are invariant with respect to f to the minus 1. So essentially I have the intersection of any of this family for any alpha, doesn't matter, or the union, or the complementation, is equal to the f to the minus 1 of the intersection of the original. So if I construct the smallest sigma algebra here, is equal to the same construction in the original set. Because you see, from this relation, essentially, I'm saying that essentially what I'm doing is if you allow me to take an equivalence relation of the space X with respect to the level set of B, I have that the space they obtain is the space Y. So I don't want to enter too much here, but if you think, if you define how the sigma algebra is built, or if you say it's in the smallest set, and you may take this observation, you observe that the image of M is a sigma algebra containing in B, and the counter image is a sigma algebra. So you see that one cannot be larger than the other. So the operation they transfer from one to the other without any. It's a biunivocal relation. Okay, I will not enter into here too much. I hope that you get the feeling. Is that okay? So you get the feeling. So the idea is that with this observation, all the operations, they can be transferred, they can be done in the original space or in the image space, and you get the same condition. Which implies that the construction of the algebra can be done in one space, and in the other, and the objects are the same. Okay? Okay, so we have this thing here. So let's go on now a little bit. one remark, which is there is a fundamental difference between the inverse of, like here, the inverse of Borel's set is Borel, which means that f is a Borel function, and f is a measurable function. You see the difference? The difference? So the difference is that
it could be measurable but not Borel, because if I have a Borel function, the inverse image can be measurable.
The differences are the sets, the negligible sets. That is only every time you get is almost everywhere means up to negligible set. So let's say this point is f equal to g almost everywhere. F is in L0 implies g is measured. So what does it mean, this condition? So if you have doubt in this condition, please say it now, because this is a fundamental thing. Doubts?
The measure of non-equality points are zero.
The measure?
Measure of non-equality of functions.
Yes, measure zero. So they're equal up to negligible set. Yes. Okay, so now the proof.
We compute the difference, summations here.
Well, I have to verify the condition, so let's do the proof. Leave one line, please. A. So I have to prove that G greater than C, or whatever one of the conditions is in L.
So this is the same that f, except in a set to 0.
So it's
same.
the symmetric difference is contained in the set where well, it's exactly what I wanted to say, just this is one line. No? So the measure of where t is greater than 0 is essentially this set plus or minus a subset of this one, which is measure 0. So I don't remember which was the other condition.
Okay. Maybe sum of
the
sum of measurable set.
We will see later. We will see later.
Okay.
This is just these are just the operation you can perform in order to give measurability. Because I give you a function, and then you is this measurable or not? Which is the answer now? There is an answer which solves the problem, but actually one has to. You can give this answer because then the people start asking something else, and maybe they could put me in trouble. So I think they can put you in trouble. So the answer, yes, it is measurable, because if you give me a function, then you don't assume the axiom of choice. Essentially, you cannot build a non-measurable function. So if you want to go deeper, means that there is a model of the real line where every set is measurable and all the axioms, not the choice, is satisfied. Okay, so you cannot build a non-measurable set in a constructive way. So this is the short answer. But actually, the long answer, the answer they want is that, well, you prove me that it's measurable by hand. For example, is the limit of continuous function measurable? You do the computation. Then you have to prove. But certainly I know, because the limit is an operation which builds something. And if I build something, I don't use choice, for sure. Is that, are you comfortable with this? This is your feeling, because it depends how you feel the situation. So the answer is yes, but you cannot give that answer, you have to prove. So what we are doing now is just to prove. So f is now 0 is equivalent So let's say for all, let's say like this, for all D measurable, F is measurable is equivalent to F restricted to D is in L0 and F restricted to the complement of D is in L0.
Excuse me, why this proves the point A?
Pardon?
Yeah, why is this line prove?
Because the measure of this set is, well, the difference is, so these two objects means that GC minus FC is equal to 0. FC, okay, is equal to 0. Because these are two disjoint subsets, they are contained in a set of measure 0. And then it means that the set is set here, which is this set minus this set as measure 0.
But we want that the measure of G greater than C itself is 0.
No. No, we want that this is a measurable set plus or minus something.
Yes.
And then it's a measurable set, this guy minus this guy plus this guy.
Okay.
And so I'm subtracting a set of measure 0 to this one and adding another set of measure 0. So is that okay for you? So let me make a picture here. This is G greater than C. This is F greater than C. And these two conditions say that this guy has measure 0, it's here. And this guy has measure 0, it's here. So essentially this set is this guy minus a set of measure 0, which is measurable, plus a set of measure 0. Is that okay?
Yes.
B is fast, too fast, but B will have fun. Okay, so about the second. Okay, it's like here, no? F greater than C is equal to F greater than C intersection D union F greater than C minus D. And D is measurable. So if this is measurable, both of them are measurable. If both of them are measurable, this guy is measurable. Okay. You see, there are just tricks in the algebra, no? Okay, so now that we have some more fun. So at the end, the idea is that the set of measurable functions is very large. So let's go with sum and multiplication. I prefer to, well, I think I will give another condition of measurability. Which is very useful. Is that mine? I think so. So let's say if A(n) contained in R dense, f to the minus 1, sorry, f greater than A(n) is measured. So if I have a dense sequence in R, the counter image is measurable, implies a countable dense sequence, implies that f is measurable. Clearly, this direction is trivial, it's the opposite.
Does this mean the set of x such that f of x is greater than an for every n?
Yeah.
I mean there are two quantifiers.
Which one?
Here, because for every n, this set is measurable.
Yeah, but the sequence is fixed.
Yeah. I mean for a fixed sequence.
Yeah.
For every n, this set is measurable, or or f of n, the set of x such that f of x is greater than all ans.
No, that one is cannot be
every-
because it's plus infinity
for every-
intense.
Yes,
The
every c is limit point of this.
Yes. Yes.
For, let's say, for every n is like this. I should be outside the
Yeah.
And actually, if I want that, okay, if I want to be correct, this should be fixed, then sequence, then we have the equivalence. I just wrote, so if I want the formula correct, should be like this. So, A, N are dense, then F L0 is equivalent to, for all N, this guy is measurable. And now it's out. This is the correct one, yeah. But you write it with the one idea and then how to do that?
Because every point in R is a limit point of the
Exactly.
sequence.
Exactly. So essentially, let's say, well, if so let's say C plus infinity being dense is the intersection of an less than C, an plus infinity. And then f to the minus 1 of this guy, okay, is the intersection f to the minus 1, an plus infinity. And then we will put this in the other. So in particular for rational numbers, I just need to check rational numbers. And automatically it becomes, so actually I don't need to check uncountably many conditions. I just need to check countably many conditions. There is a notation that, this is an observation that clearly is, doesn't matter, but actually is important from the point of view of the logic, no?
And for general spaces, this works for separable.
Yeah, you need just balls. So separable means ball with a radius. So separable means you have a dense sequence, and then you take Rn, one or equal to 2 to the minus n. So the counter image of the ball, of the center of radius. I don't know the notation. Here I use a different notation, but actually it's a center xn and radius 2 to the minus n. You require to do that. So yes. You never, in any case, the philosophy is that you never do uncountably many operations. Well, maybe you are allowed to do for some reason, but actually everything can be computed by countably many. That's the theory. So let's see now the theorem now. F, G are in L0, then, so for all alpha, beta in R, alpha F plus beta G are measurable, and F, G are measured. So actually here, if they assume values which are plus infinity, we have just to be sure that in this computation you never get forms which cannot be decided. Yeah, I prefer to do it is there is another thing. Sometimes when we have 0 times plus infinity, they say it is equal to 0. But in any case, you always can handle these limit cases. So in our setting, when they are finite almost everywhere, that object is defined. Because we assume that the values are in R up to a set of measure 0, where maybe they are not defined. Okay, so let's prove it. So the philosophy of what this proves is always to write the set in a smart way, no? So point 1, let's say f. Let's start with alpha step 0. Alpha f measurable. So we don't need to take the alpha over there.
Equivalent if greater than C. Yes.
Okay, I can assume, no? Otherwise I put the minus in there. Okay. So I have only now f plus g. Well, let's see. If I take first the set where f is greater than d, well, only countably many. Well, let's say with d, okay. D, and then
C minus D?
Yes. G. G. C minus D. No, the other one. G.
fine, but then
We
this
can
is a
take
particular
D
case.
1 over N.
D is reference.
We can take D 1 over N for all N.
But it is negative, and it is to value. And then if it is 1 over n, then here you say just things which are close to g.
By
Now,
1
maybe
over
C is very 2g, 2c, you don't get it.
D reference.
D.
Okay, let's put first here. This is a particular, but then they cannot be enough for fixed d, no?
Yes, like here I'll be rational.
D
Okay, let's, yeah. Okay, now can't eliminate. Well, then at the end, this is the guess that one has to prove actually this always, no? You agree, no? It's not that. So, the rational, yes. So, okay, the guess is correct, but actually you have to prove.
Yeah, because if plus g of x is greater than c, then we can choose a rational number between this value and c, and we take this value to.
So you say to fix a rational number here.
No, what I say, we have f plus g of x is greater than c.
Yeah.
Okay, so so at least.
No, one is free. This fact is free.
That's the union of
This is the. These are all the. These are essentially where in D has all the set where f is defined. So if f is a value, so let's say if f is equal to a, okay, then you are in the set G should be greater than C minus a. But then it means that you take dot is greater than C minus epsilon half. So you can take a rational here, no? So if I lower, so if I upper a little bit, the q is minus q, minus some d rational. Because rational are dense and, sorry, not like this. Let me say like this. This is, so it means that G is greater than C minus D with D rational. There is a rational which I can put in between. No? Because there is some space. And in this set, it means that D is less than A. So here is greater than D. So I'm certain inside one of those sets.
Can we make a similar argument by saying if f plus g is greater than c, then at least one of them is greater than c over 2, okay? And therefore, we can assume f is greater than c over 2. We can take a rational number between the value of f and c over 2, and that's d. And if the other way around, we just change.
Yeah, yes, but then one of... Okay, then is the union of two split
Yes.
in Q into two
Yes.
parts, yes. But you don't need that, you know, it seems to...
Yeah, but I mean, we will avoid all this argument about the value of f equals a.
I'm not sure.
Why? Because we will just need to double this union.
So if C, so one of the two is greater than C, so assume that F is greater than C half.
Yes. So there is a natural number between the value of f and c over 2. Sorry, a rational number.
Yeah.
Call it d.
Okay.
Okay, so
yeah.
great. So now f of x is in this. I have a.
It is larger.
Yes.
So this is smaller.
No, but
Yeah.
f is greater than d.
Okay.
Okay, so
Yeah.
now it is good now. If the other way around, I have another version of this, another union, just reversing the role of f and g. So I take this union, the same thing, but with
It can work because so this is a fixed. So fixed is D, and then which are the value so which are the value of G such that they do match with this in this set? Once I give the values of F, I need to give the values of G. They are not split. Because you can say that at least one that's a necessary condition, but it's not sufficient. And so the sufficient condition is this one. If this is larger, then it should be larger. Otherwise, you have something smaller.
yeah.
And then, okay, now the only trick is that you have that you just take the rational. The rational is sufficient because you have an open interval here, which means you can put a rational in between. So that's the. Okay, so about the product.
Can we just prove it for the f squared? That's easy because we can take the square root.
Yeah, that's as the book does. Yeah, but it says the following that fg is one. Well, actually, there is one trick you can do the same. So here is divided by d. No? And then it works the same formula. But here the book says that it's f plus g squared minus f squared minus g squared. Now we know that sum and subtractions are measurable operations, and also multiplication. So we need just to prove that the square is the only operation, so the square. So then only f is in L0 implies f squared is in L0. Well, that's easy because f squared greater than c is, well, f should be greater than square root of c, or f should be less than minus square root of c. So it's fine. Okay, so far so good, because the space of measurable function is what is called, well, it's a linear space, and then it satisfies also the operations, and hence, well, also one of the, we'll see also that is really much more of a plasticity. Okay. Okay, so the next, the general case, actually there are problems here in this proof.
Which one?
This one is tricky. It's this one. This is a very fundamental trick. So the idea is that you always use the rational, and then, okay, you write the corresponding condition, but always do for rational numbers, or in any case, a dense sequence, which depends on which one. So now, let's do the following. Proposition. F is measurable, and G is Borel. Which means that G to the minus 1 of the Borel sigma algebra is contained in the Borel sigma algebra. Then G composed to F is measured. This is a fundamental theorem because now with composition you can really do a lot, construct a lot of functions, no? Well, but this is what? It's F to the minus 1 of the set G to the minus 1 of the set C plus infinity. Now this is Borel, and we know that the counter image of Borel is measured. So we use that G to the minus 1 of Borel is Borel, and F to the minus 1 of Borel is measured. So, okay. And I think then we will make maybe a okay, just a few results, and then I prefer to restart a little bit from the beginning and see what we have done so far, because we are almost at the integral. Okay. So the example is F compose G with F, G, sorry, the F, G are measurable, but F compose G is not measured. Okay, before arriving to the point, or to the example, why this can happen?
Because the inverse of a measurable set need not be a measurable set.
But why? Yes, you're right, but why? Yeah, so the hint is correct. So the idea is correct.
Simply because if I take a function f and I map an unmeasurable function to a constant, so we have an unmeasurable, an unmeasurable set z. I map it to a number, okay, and all other.
They don't care, okay,
yeah.
Was 0, whatever.
Yeah. So now we have a point is a measurable set of measure 0, and the inverse image is an unmeasurable function by an unmeasurable set by definition.
Yeah, but then the function is not measurable, no? Because the counter 0 point is not measurable. But we have the example, you remember, that when we wanted to prove that you have sets which are not Borel, but measurable. We did the following. We take a set of measure 0 non-measurable sets, which is mapped by a Borel function, actually a continuous function, into a set of measure 0. So the function was invertible. So on one hand, we prove that there is a subset of measure 0, of a zero measure set, which cannot be Borel, because its image is not Borel, is not measured. On the other hand, you see now the opposite. You have a set of measure 0 whose counter image is a set which is non-measurable. So okay, let's see the trick level. So here we have this z. So you remember it was the Vitali function, let's say the Vitali function. And this is the Cantor set. Cantor set, if you remember, no? And this function was x plus the Vitali function. Now the 1/3 Cantor set becomes now a set of length 1. So the compact set of length 1. So if you remember, so let me try to do a picture a little bit better, because otherwise you don't see it. So if you remember, the construction was like this. Okay, and now the map is so you have these pieces here. So it's always filled by intervals. The function is growing, and it happens that the measure of these intervals has length 1 and the limit point is 2. So the measure of the Cantor set is a compact set of length 1. We know that we can build a non-measurable subset here. So let Z be in x plus 5, so identity plus 5 of this set K. This was the construction. So now we used before as follows. The counter image of this non-measurable set is a subset of the counter, which has measure 0. So it is measurable. It cannot be Borel, because this function has a continuous inverse. So it's a continuous, strictly increasing function, the inverse is continuous. If this were Borel, then its counter image would be Borel, but actually is Z. Okay? And now we use to prove the statement that the counter image of measurable set cannot be measurable, because this set as measured is a sub. So the counter image of this set is a subset of K, so it's measurable, but its counter image is Z, which is non-measurable. So set of measure 0, they make trouble. The function, in other words, in these sets, the function can be defined as you want, because everything is defined up to set of measures. And so the only composition you are allowed is with functions which are Borel or continuous. Continuous function is Borel. Okay, let's. I noticed it was a little bit dense, so maybe I prefer to. Let's start from the beginning and see what we have reached so far. And we have a scheme of all the situations. So the point 1, so starting point. Outer measure, yes, outer measure. M star, which is based on the length of intervals. We know the length of intervals will cover, take the infimum of this cover, you have M star. Then,
a restriction of measures, the
measurable sets, the definition of measurable sets, the one that essentially I can cut These are the decomposition I'm allowed to do. So it's M star of A is the decomposition, no? Okay, now from this one we have a plethora of results. So we have that we define the sigma algebra,
Yes.
no?
Sigma algebra.
And then that what is M star restricted to a sigma algebra is sigma additive, so it becomes a measure. Is a measure. So which means it's a sigma additive. And then we have some properties, no, of the sigma algebra. So for example, the Borels are contained, so open or Borel sets are in L.
There are sets with measure 0.
Yes, and essentially we have the regularity up to negligible sets, which means that, okay, you add the subtract set of measure 0, and essentially you have nice sets, which are intersecant with the intersection of open, or essentially you can approximate with open outside, closed inside, and this means the regularity. So it's true that it's a very large family of sets, but actually you can always use good sets to approximate them. This is the regularity. And here, well, it says that they are so large that I'm fine with all the functions, the elementary functions I need. And about the measure, we have the sigma additivity, which is in the definition, and I don't know what we do, the outer regularity of the measure, the inner regularity, so regularity of the measure. So this means that if I need to give a value to a set, well, I can use the open outside, but actually since a measure, I can use also the closed inside, or the common at the end. So I'm very fine in computing. At the end, I need only to compute open, and then take a limit. So once we have this object, well, there are some bad cases, and here we open the bad cases. And well, all bad and also strange cases. So the strange case is
non-measurable set.
is the bad. I think it's the worst. The strange are these functions and sets which they don't preserve the measure. So essentially, well, the measure doesn't see dimensions and structure. You can change the structure and then the measure is always the same. So let's say here, our example was the Cantor set. Cantor sets. And the bad cases are non-measurable sets.
Is always one inside
Hmm?
and there is always one inside a measurable set.
Or non-measurable. If you assume the axiom of choice, yes.
Okay.
In any case, you can prove by cardinality that there are non-measurable sets which are not correct. Because the part you have a measurable set of measure 0 which is uncountable, and is the Cantor set. So the power set of this set, each element of the power set has measure 0, so it is measured. And this is the power set of an uncountable set. On the other hand, the Borel sets are constructed by countably many operations on countably many sets. So its power is the continuum. So this is a measure theoretic proof, sorry, set theoretic proof that you have more sets. But this requires a little bit, because the problem is the following. When you go to an exam and they ask you prove it, well, you can give this proof. But maybe there is somebody start asking you, okay, let's talk about cardinal numbers. And then you can be in troubles, no? Or ordinal numbers, and then so it's better if you give an explicit example. Well, the example is the example. That's it. They don't ask you. It's always tricky, no? Either you want to show that you are the best mathematicians and risk a little bit, or you just require to say, but what I know, I know. If I don't know, I'm sorry. Okay, so far so good. This is more or less what we are now. So we are fine. And now the next step is, since we want to have the integral, now we have measurable sets, and then we go to measurable functions. And so far what we know is that measurable functions, well, we know when a function, so that the building block is the characteristic function, the indicator function. Is measurable, so let's say this is L0, a measurable set RL is in L0 is equivalent to A is in L. This is what I want. This is the building block. It's always the building block. Then we discover that essentially the algebraic operations are fine. What we prove. So algebraic operations are fine. Fine and composition. With whatever. Okay, so let's see. Here the definition is f to the minus 1 of any open set is in F. Well, let's give this definition. So, but the aim is always to reach the integral, no? Because at the end I need a number. And so now we go a little bit further in this construction in order to prove that also limits are fine. And then we have to compute the definition of integral, which I suggested at the beginning. So it's that sum, you have to prove it. You go to sum. I think this today was heavy, so let's stop here. Okay, I'm done. Okay.
So we are going to do next class. We are going to discuss the limits.
Yeah. We have still to, because I thought I felt that today was already heavy, so I decided to we add some more operation we can do with the measurable function, and still we get measurable function, which is the sub, the in, sub, limits, and that's it. And then after we have this, the next, we have some regularity theorem. I forgot to say that. The regularity here, this is measure, regularity is equal to measure, means that also this function, they cannot be too bad. Because just imagine that if you think everything is constructed by those, and those are constructed by sets, these sets are essentially open sets, so essentially I'm always like a continuous function, which is true. For a measure, essentially the measurable functions are continuous functions, but do not tell this in the exam because they vary. But this is the feeling. The feeling is that they cannot be too bad, because these are not too bad. These are not too bad. This guy then cannot be too bad, and these guys are the building blocks.
How far we are going to reach in the course?
if we go very far, we do the proof, because last time I didn't finish with the proof of Gini, Radon-Nicolin theorem, and hand-band decomposition because of time. But if we reach this level, essentially, so the idea is that we finish with the Lebesgue measure all the structure, and you see I'm trying also to present with something where you don't see R. So R is not going to appear explicitly. We have this Lebesgue, but at the end, all the operation will not be dependent on R. So at some point becomes any measurable space, any measure space, and we do the sets. Once we have we do these three theorems. Once you have this theorem, basically you have all the basic knowledge of measure theory. If we are very good, depends. Then we go a little bit deeper with some advanced theorem in measure theory. And it's called the Hausdorff measures, Hausdorff dimensions, and disintegration theorems, and Minkowski content, all these objects like that. But this is, I don't believe this. But since I'm going to cut the Riemann integral because it's useless,